Imagine imagine testing the code you just wrote. You hit run, you watch the console, and you're pretty sure it's secure.
Right, because you wrote tests, they passed, you followed the best practices.
Exactly. But what if instead of just being like pretty sure, you had absolute zero doubt mathematical proof that your endpoints were locked down?
Yeah, a scenario where your security perimeter isn't just based on, well, an assumption or a passing unit test. It's a literal, undeniable mathematical certainty.
Before the code even runs. And, I mean, while you're wrapping your head around a system that mathematically guarantees its own security, that exact same code is running up to 26 times faster than your current local setup.
Which is just a massive leap.
It really is. So today we are going on a deep dive into this incredibly dense, just fascinating README file for an open source project called XRanger. And for some context here, XRanger is a local Wrangler-compatible substrate designed specifically for the fork join and Eon worker stack.
Yeah, and for anyone who might not be super familiar with it, the fork join and Eon stack is essentially this distributed execution environment.
Right.
And developers who are building for that kind of architecture, they need a way to run those cloud-native functions locally on their own hardware. So that is the exact gap XRanger is trying to fill.
Okay, let's unpack this because honestly, even if you aren't spending your days deep in back-end infrastructure or, writing serverless web workers, the sheer performance leaps we're looking at here and the honestly sci-fi level security concepts in this document, they're going to completely change how you think about software.
Absolutely. But to understand the leap, we really first have to look at the baseline.
Right, where we're starting from.
Exactly. Developers building cloud workers generally use a tool called Wrangler to test their code locally. And Wrangler uses a V8 isolate sandbox, specifically Miniflare worker, to completely emulate the massive global cloud runtime right there on your laptop.
Which, I mean, it prioritizes perfect compatibility, right? Like over raw performance.
Yeah, exactly. It recreates the entire atmospheric condition of the cloud environment so the worker feels at home.
The analogy that comes to mind reading through the source is Wrangler's sandbox approach is kind of like testing a toy boat by flooding your entire house with water.
That's a bright way to put it.
Like, yeah, it's accurate. You know exactly how the boat floats, but it is incredibly heavy.
And messy.
Right. And XRanger takes what the developers call the honest path. It doesn't build the sandbox at all. It just imports the worker module and calls the fetch function directly.
Right. By dropping that isolate, XRanger hands the socket directly to the code. There is no heavy runtime emulation sitting between the network request and your worker. The execution just happens natively.
Which is huge.
It is. The performance difference we see from that architectural shift alone, I mean, it changes the entire baseline of local development.
Yeah, because if emulation is the bottleneck, stripping it away has to fundamentally alter the stress test results. And the benchmarks in the source material, they map this out so clearly. So running the exact same worker on the exact same host hardware under the exact same load, the standard Wrangler development server maxes out at 2,179 requests per second.
Which is decent for local.
Yeah, the latency at the 99th percentile sits around 53 milliseconds, which, for testing a local web app feels totally fine. But then they run the same code through XRanger using standard HTTP. Suddenly, the throughput jumps to 40,437 requests per second.
Yeah, an 18.6x speed up simply by adopting that honest path.
Insane.
But the thing is, XRanger doesn't rely solely on just the lack of a sandbox for that speed. It actually utilizes a custom Rust manager on the front end, paired with this ingress path called Gnosis hearing.
I want to pause on Gnosis hearing, actually, because going from 2,000 to 40,000 requests, that implies something structural is happening at the system level. You don't get that just by stripping away a JavaScript wrapper.
No, you don't. What it does is bypass standard kernel networking bottlenecks entirely.
How so?
Well, in a traditional setup, when a network packet arrives, the hardware interrupts the CPU, right? Then the kernel handles the packet, allocates memory, and then passes it up into user space where your application finally reads it.
Lots of steps.
Exactly. It involves a massive amount of context switching, but Gnosis hearing leverages these advanced asynchronous I/O principles to essentially talk directly to the hardware ring buffers.
Oh, wow.
Yeah, it processes network events almost entirely without that traditional system call overhead.
Which completely explains that HTTP jump. But the source material pushes it even further. When XRanger switches away from HTTP entirely and uses UDP transport, the throughput hits 57,188 requests per second.
staggering number.
We're talking 26.2 times faster than the Wrangler baseline, with latency dropping from 53 milliseconds down to a near-instant 1.6 milliseconds.
Right, and achieving 57,000 requests per second locally, it forces a complete rethinking of how data physically travels from the outside world into the worker. The speed requires an evolution at the transport layer itself.
Right.
So X-Ranger implements what they call a polyglot at the wire design.
Yeah, a single fetch handler, right? Like
Yeah.
one exported piece of code just sitting there waiting for a request, simultaneously answering requests from 3 entirely different network transports.
Exactly.
It listens on standard HTTP, it listens on a custom TCP AON flow, and it listens on a UDP AON flow, all mapped to the exact same handler.
Because the underlying code, it doesn't care how the invocation arrived. It just simply executes the logic.
See, I have to admit genuine confusion here, or at least like a strong desire to push back on this a bit.
Sure.
Why do we need UDP or custom TCP lanes for web workers at all? I mean, HTTP is the undisputed universal language of web traffic. Browsers use it, APIs use it. Why are we reinventing the network wheel to invoke a simple back-end worker?
Well, what's fascinating here is the concept of a deployment contract that's driving this architecture. The developers explicitly state that for standard local development, Rust over HTTP is the ideal path.
Okay.
It's standard, it's heavily tooled, it's easy to interact with. But when this architecture scales out over the actual web, across the EON architecture, diversity in transport rules.
Meaning they need different lanes for different types of traffic.
Exactly. They utilize these specialized TCP and UDP lanes for invocations where latency is the absolute most critical metric.
But what makes those specific lanes so much faster than a standard HTTP connection? I mean, a packet is a packet, right?
It's all about the protocol framing. Standard HTTP requests carry significant baggage. They require formatting, parsing, and they carry extensive headers, host, user agent, accept types, all of that.
Right, right.
The custom TCP and UDP lanes discard all of that. They rely on a custom 10-byte frame called a conscious stick, and inside that tiny frame sits a heavily compressed JSON and base64 payload.
Wait. Standard HTTP headers easily take up hundreds of bytes. If you only have 10 bytes of framing, you are flying completely blind from a traditional networking perspective. How does the system even know where to route the packet or what state it belongs to?
That is the brilliant part. It shifts from stateless routing, which is what HTTP is, to highly state-aware edge routing.
Okay, walk me through that.
Those 10 bytes don't need to carry the entire context of the universe like an HTTP header does. The conscious stick acts as a compact state pointer. It references an already established, pre-negotiated connection state within the EON flow.
Ah, I see.
Yeah, because the context is already known by the system, the packet only needs to deliver the raw delta, the actual invocation payload itself.
So the developers, they call this skipping the envelope ceremony.
Exactly.
They aren't wasting 450 bytes per request, formally introducing the packet, asking for permission, listing its credentials over and over. It just executes, which makes it mathematically perfectly sized to fit inside a standard 1200-byte network transmission unit, or MTU, without any fragmentation.
Right. 0 bytes are wasted on ceremony. The packet hits the network interface and triggers the worker invocation with almost 0 intermediate parsing.
But taking a step back here, because we have stripped away the V8 emulation sandbox entirely, we are opening raw, unsandboxed UDP and custom TCP ports directly to a local process, processing 57,000 requests a second with minimal packet inspection.
It sounds risky.
It really does.
Yep.
From a traditional networking standpoint, having an honest path with no walls around it sounds like handing the keys to an attacker and just walking away.
Yep.
How does X-Ranger actually keep this environment secure?
Well, the absence of a traditional sandbox means the network layer itself must become the absolute enforcement mechanism. The system implements what they call a mesh policy.
Okay.
It relies on a port-authenticated mesh. This is a temporary network deployed per request, operating on a strict default deny basis.
Meaning no open doors by default. You have to explicitly whitelist the port, and even then, the request must survive a rigid 5-gate ordering process.
Right.
The source outlines these gates clearly. Gate 1 is the overlay prefix match. If you hit a blocked region, the request is dropped immediately.
Yep.
Then Gate 2, path whitelist check.
Yeah.
Gate 3, HTTP method verification. Gate 4, authentication header validation. And only after surviving those 4 structural checks does the request hit Gate 5, where it's finally delegated to the interfetch handler.
And the speed of this execution requires the security perimeter to be incredibly transient. The security mesh only exists for the fraction of a millisecond that the request is active.
Here's where it gets really interesting, though. To help conceptualize a perimeter that just blinks into existence for a microsecond and dictates absolute law, the developers use this brilliant analogy in the source text. They compare a deployed mesh to a domain expansion.
Yes, the anime concept.
Right, specifically from Jujutsu Kaisen. The idea of a temporary, bounded region of spacetime where the user's specific rules and invariants are absolute.
It's a very fitting analogy.
It is. Inside the mesh, the developer's policy is literally the laws of physics. The whitelist is the only mathematical scene that allows entry. Defensive overlays, which the developers call ICE intrusion countermeasures, they are layered onto that mesh, allowing you to block specific paths dynamically without collapsing the entire domain.
The conceptual framework is definitely useful, but the underlying mechanism securing that domain is the true breakthrough here.
How so?
This mesh policy is not validated by standard security testing. They don't just run a suite of unit tests and assert that bad requests were blocked. The entire policy logic is backed by 10 zero-sorry Lean theorems.
Okay, for those listening who might not be deep into theoretical computer science, Lean is an interactive theorem prover. When you write code in Lean, you are essentially writing mathematical proofs. But what does zero-sorry mean in this specific context?
So in the Lean environment, sorry is a specific macro. It acts as a placeholder when a developer hasn't quite figured out how to finish a complex mathematical proof yet.
Like saying, trust me, I'll figure this math out later.
Yeah. Exactly. Zero sorry means there are no placeholders, no assumptions, and no unproven states anywhere in the code. Every single theorem dictating how the network mesh operates is fully mathematically proven to be true.
But, I mean, how does a mathematical proof on a piece of paper or in a compiler actually stop a bad network request at runtime? Like a math formula doesn't actively tackle a UDP packet.
No, but the proof dictates the physical architecture of the compiled binary.
Oh, I see.
Because a theorem like, say, empty portless seals region or authentication restricts ports is mathematically proven within the build pipeline, the Rust runtime simply refuses to compile any network routing path that could violate that proof.
That makes sense.
The binary fundamentally lacks the code paths required to breach the invariant. So the runtime isn't making a decision about security on the fly, it's just executing the structural physics dictated by the math.
Okay, so if a system is mathematically proven to be perfectly secure under its own structural laws, how does an attacker even attempt a breach? I mean, you can't just brute force a password or eject SQL if the physical path to the database just physically doesn't exist in the compiled logic.
You can't.
So you have to somehow exploit the structural physics of the mesh itself.
Exactly. It elevates the security landscape from a software problem to this incredible game of cat and mouse at the level of structural topology. The document details the defender's overlays, the ICE we mentioned, but it crucially outlines exactly 3 structurally distinct bypass surfaces that attackers can theorize.
The anti-IC.
Right. They call these bypasses anti-IC.
The mechanics of these anti-IC attacks, they read like theoretical physics. The one that immediately jumped out to me is the xenonic approach.
Yeah.
It's derived directly from Zeno's paradox, the ancient Greek thought experiment, where to reach a destination, you must first cover half the distance, then half the remaining distance. Infinitely approaching, but mathematically never arriving.
Yeah.
How does that translate to a network attack?
Well, the source describes the xenonic bypass mechanism as a numerator-preserving, denominator-doubling contraction.
Which is quite the mouthful.
It really is. But basically, instead of attacking a specific port directly, the attacker manipulates the mathematical boundaries of the mesh. They incrementally shrink their attack surface, halving the logical distance to the restricted port with each invocation.
But because of the mathematical rules of the mesh, specifically a theorem called barrier never reached infinite steps, the attack can run infinite finite iterations and mathematically never land exactly on the restricted port.
And the attacker utilizes that limitation. Because their invocation surface asymptotically approaches the target but never technically touches the restricted coordinate, the defender's mathematical tripwire never fires.
Wow.
Yeah, they bypass the alarm by hovering infinitely close to it without triggering the actual state change.
That is wild. If we know that attack is possible, how do the other 2 bypass methods operate?
Well, if we connect this to the bigger picture, the other 2 anti-IC surfaces manipulate different mathematical primitives entirely. Okay? The first is the overlay hole bypass. This exploits a theorem called orthogonal overlay stack additively. An attacker mathematically maps out the defender's ICE coverage, finds the exact disjoint space where the coverage mathematically isn't, and stacks their attack footprint perfectly inside that blind spot.
Literally finding the microscopic gap between the scales of the armor,
Exactly. And the final bypass is temporal, the clock rate side channel.
where time itself becomes a structural vulnerability.
Precisely. The attacker samples the port surface at a strictly faster tick rate than the defender's mesh policy is designed to observe.
Ah, so they're moving between the frames.
Right. Because of a theorem named deficit unbounded in horizon, the attacker operates between the frames of the security camera, essentially. They accumulate unobserved states over time, effectively slipping past the mesh while the defender is between processing cycles.
So if I'm deploying a system, and I am staring down 3 mathematically distinct, theoretically proven bypass methods, how do I actually secure the application? If I patch the xenonic approach, does that secure the mesh?
It does not. Hardening the code against a spatial contraction attack like the xenonic approach does absolutely nothing to prevent a temporal attack like the clock rate side channel.
Because they're completely different vectors.
Right. They rely on completely different mathematical logic. You cannot structurally block all of them simultaneously without completely collapsing the network mesh and rendering the application useless.
Which necessitates the creation of what they call honey pit traps. Instead of trying to build an infinitely solid wall, you deploy a trap overlay. The honey pit absorbs the attacker's traffic, simulating a successful bypass without ever leaking the actual restricted ports.
Yes.
It tricks the attacker into believing their anti-IC sequence worked, keeping the real, vital payload structurally isolated.
It is active mathematical deception.
So if you're listening to this and thinking, I just write JavaScript for a living, why do I care about lean proofs and temporal network bypasses?
Right.
Here is the practical reality. We have blazing 26x execution speeds. We have native unsandboxed execution. We have domain expansions and Zeno's paradox cyber attacks. But if a developer has to manually configure all of this math to deploy a simple worker, adoption will be 0.
Absolutely 0.
So how does this system bridge the gap to actual production?
The compilation process is the key to making this usable. If the X-Ranger runtime had to read a text-based configuration file and calculate these complex mesh rules dynamically on the hot path for every single incoming 10-byte frame, the performance would just plummet.
Right, text parsing and dynamic policy evaluation are incredibly slow.
So they shift the heavy lifting entirely to the build step.
Okay, how does that look for the developer?
The entire mesh policy compiles down to a microscopic .bw binary artifact before the code ever runs. It is completely deploy invisible to the developer.
The document highlights a Vite plugin specifically designed for this workflow. And Vite is a massive build tool in the web ecosystem right now. So a developer just writes their code, hits save, and the plugin automatically compiles the mesh policy into that .bw binary in the background.
And crucially, the compiler generates a cryptographic SHA-256 fingerprint of that compiled bundle. This mechanism relies on a theorem called compile fingerprint is content addressed.
Content addressing is such a beautiful concept. It means the fingerprint isn't just like a random ID tag. It's mathematical derivative of the logic itself. If the code is identical, the fingerprint is guaranteed to be identical. There's no variance.
Yeah.
So how does that impact the deployment cycle?
Well, when the deployment tooling prepares to push your worker, it simply checks your local SHA-256 fingerprint against the fingerprint already live on the server. If they match, the system mathematically knows the logic hasn't changed.
So it just skips it.
It skips the redeployment entirely. The math proofs we discussed earlier guarantee that 0 network overhead is wasted on redundant updates.
Which directly impacts the everyday friction developer's experience.
Yeah.
I mean, in standard Wrangler, executing a process to grab an authentication token takes roughly 60 milliseconds.
Right.
It feels fast enough until you experience X-Ranger doing the exact same task in roughly 2 milliseconds.
It's night and day.
It is a 30x speedup for a basic local developer workflow. Local key value database reads hit a 4x performance increase. The sluggish, heavy feeling of emulating cloud architecture locally is just stripped away.
It completely removes the friction from the developer experience while simultaneously upgrading the security model from assumed safety to mathematical certainty.
So what does this all mean? The underlying mechanisms we use to build the internet are fundamentally evolving. We're looking at a future where we move away from bulky emulation sandboxes pretending to be the cloud. We're shifting toward architectures communicating across multiple transport lanes simultaneously, dropping the bloated HTTP envelope ceremony for hyper-efficient 10-byte frames.
Yeah.
And most importantly, We are moving toward a world where the security of our endpoints is dictated by zero-sorry mathematical proofs, rather than just a checklist of best practices.
The industry is shifting from trusting the system to actively proving the system before execution.
And that leaves me with this final thought for you to ponder. If our local development environments are naturally shifting toward these unemulated, ultra-fast, mathematically verified local executions, what happens when these specific concepts scale up?
That's the real question.
Right. What happens when a system like X-Ranger bypasses local development entirely and replaces traditional cloud execution environments at the global edge? If a temporary domain expansion mesh is mathematically perfect, proven by zero-sorry theorems to deny unauthorized states, do we even need traditional firewalls anymore?
It's wild to think about.
Do we need complex cloud sandboxes or virtual private clouds dictating network traffic? Could the actual future of the internet simply be directly connected, mathematically verified, peer-to-peer applications running at native hardware speeds? It fundamentally challenges everything we assume about web architecture. The next time you hit run on your code, consider what it would feel like to not just assume it works, but to mathematically know it for a fact.